doing this, I'm recording this. So I gave you guys this to go by. This isn't the one out of your book. I just want to do this psychedelic stuff. Let me get the PowerPoint open. So in this PowerPoint that I've been building, this is all the stuff I said I'd give you on the test. So there's the stuff on polarity. There's the acid base, gas evolution reactions. So this is what your book gives you on how to assign oxidation states. The thing you have in your hand, well, I meant to add that to this too. I just think it's a little more straightforward. I think this makes things sound really much more complicated than they are. But oxidation states are very similar to charges that we talked about. The only ambiguous part is what charge would you assign a atom when it's in a covalent compound? Ionic compounds, the charges are obvious. Covalent compounds, they're not. So one thing I want to say is, you see this copper here? That'll have it. So these kind of aren't real things; they're kind of bookkeeping things. Oxidation reduction reactions are electron transfer reactions. Electrons get transferred from one place to another. That doesn't happen in every reaction. So this sort of bookkeeping game helps us decide which atoms in a reaction lose electrons and which atoms in a reaction gain electrons, aka that thing that happens in oxidation reduction reactions. So this is chapter 8.9. If you want to read a little at the beginning, maybe the beginning of that chapter, maybe it helps. But these two things right here, this one's saying here's a metal by itself. That's usually in a reaction we would have Cu and then an S in parentheses. When it's like that by itself, it has an oxidation state of 0. So this might seem a little abstract, just follow me here. And this one, this covalent compound, the Cl2, that one has a 0 as well. And the way this is stated is it's an elemental compound. If it just has one type of atom in it, for instance, if that was copper with an S in parentheses, that would be a chunk of copper. And it would be all copper, it would be nice and pure because it's just copper. In that case, copper has an oxidation state of 0. In this one over here, it only has chlorine in it. It's nothing but chlorine. So it has an oxidation state of 0. So let me leave what an oxidation state is just a little bit abstract, and then I'll show you the process, and I think it's a lot more obvious than it is. And this is what I just said. If you've got an ion and it's by itself, which is generally most of the way we talk about ions, the oxidation state is the charge on it. So that part should be straightforward now. If I ask you what is the charge on calcium, you would say 2+. If you see calcium in an ionic compound, its quote oxidation state is 2+. If you see chlorine as its ion in an ionic compound, its oxidation state is the same as its charge. So I know that's a little abstract. H2O, well, now we get to these rules where I think it's easier to show you the process, but you can read this and see what the assignments are. I think this thing that I just gave you, I want to add that. Hold on. Let me add that to this PowerPoint while we're sitting here. There. But I think if I just take you through this process, it'll be obvious, more obvious how you assign observations. I sort of have my own method that I've developed over the years, and that's one here. Notice in the top right there, practice problems for oxidation reactions. This is for our book. So those exercises, this is what I usually write on the board. Exercises. But it's these that I'm going to show you. I've got these as examples here. There are more examples in 75 and 76. But let me just show you this process. All right. So you've got SNO2 and you're asked, what are the oxidation states of the atoms in this molecule? The first thing you would do for this one, do this thing you already know. You can split it out into the 10 ion and the 2 oxygens. And this is how I showed you how to do this before. This is just an ionic compound. So the oxidation states here are going to be the charges that you already know. So if you split that out, you've got 2 oxygens there. It's -2, -2. All right, so the 2 -2's add up to -4. And now you're going to ask yourself, what am I going to put on the SN ion? Also note here that SNO2 doesn't have a charge there. So these need to add up to 0. If there's a charge up there, they need to add up to whatever that charge is. But I'll do an example like that next. So if you look at this and you go, okay, what's the charge on 10? Should seem very familiar to stuff we've done already. What needs to be the charge on the 10? Or I should say what goes here in this parentheses to make this statement true.
It would be 4.
Yeah, it's a +4. That's how you make that equal 0. And since you only have one 10 ion there, the entire +4 goes on to 10. So the charge, but let's say oxidation number. Oxidation number is a synonym for oxidation state. I guess I used oxidation number in this when I made the PowerPoint. Oxidation state is the same thing as oxidation number. So there's the answer. Oxygen is 2 negative in that ion compound, and 10 is 4 plus. So there you go. 4 plus for 10, 2 minus for O2. Or for oxygen. Oxygen is 2 minus. If you had Ta2O3, it would be the same way. You put your 3 oxygens down, they equal -6. There's no charge on this, so it's 0. And then you go, okay, I need a +6, and you split that +6 into the 2 TAs. TA. All right, KBrO4. This one is this is where the real twist is. The BrO4 is one of those polyatomic ions.
Do you have the slideshow posted somewhere?
The what?
This
I'm going to, yeah. I'll upload this so you have it. I do it right after class when we're done with it. So you will have this PowerPoint. But again, the first thing you want to do with these polyatomic ions is that you know that K on the front is going to split out and be a +1 ion. Something you already know from the periodic table. Where potassium is, K on the periodic table, it's in that first column. So it's +1, and that tells you that the BrO4 ion is going to be -1. So I've already assigned those charges. And where we are now, we can go ahead and say that potassium's oxidation state is +1, because that's just literally what its charge is. It's an ion, so it's the charge. But let's continue with BrO4. All right, now we do this again. We split them out into the Br and the 4 O2s. Oxygen is almost always the key to these type of things, to these polyatomic ions. So you take your 4 oxygens, you add them up, you get -8. Notice that this is, the BrO4 is a -1 charge. That goes over here on the other side of the equal sign. And now if you look at this, what has to go in this parentheses here to make that math true?
7.
Yep, +7. +7 plus a -8 will be -1. you get +7. And there's only one BR there, so that whole +7 goes on the BR. So, summary here is, in this compound, KBrO4, K has an oxidation of +1, Br has an oxidation of +7, and oxygen has an oxidation of -2. Huh? Oh, you see the arrow? What goes on the right side of the equal sign is what's the charge is on the compound that you just split.
Whenever you're finding the oxidation charge of covalently bonded compound, do you always start with the metal limits?
With the metal?
Yeah.
Well,
sort of the potassium.
you're almost always going to be keying in on the oxygen because oxygen is in nearly every one of those polyatomic ions.
Okay.
But you do split the metal away from it. So yeah. Okay, I doubt osmium oxide, whatever that is on that polyatomic ion chart, but you can still do this by first splitting out the two potassiums, and there you're done with potassium. Its oxidation is +1. And you've got osmium and oxygen 4, so you're still doing the same thing. You split out your 4 oxygens, you get a -8. You see where the -2 came from? The -2 came from up here. So to make that equal -2, you gotta have a +6. That means osmium is +6. So the oxidation state of potassium is +1, for osmium it's +6, for oxygen it's -2. Here's a bunch more examples. I would kind of rather, I gave you some for practice, so I'll go over this. But look at the chromium O3 there. You split the oxygen, there's 3 of them. There's no charge there, so that it needs to equal 0 over here. Therefore, you got to put a +6 here. There's only one chromium, so it's +6 for chromium. So the answer is down here in the green box. Oxidation state for chromium here is +6, and for oxygen is -2. That's the only 2 things in here, chromium and oxygen. This one, if you just split these out, this Hg2+ is on that polyatomic ion list that I'll give you on a test. But if you split that out, you got 2 Hg+. You see this Hg2+. So if you split that out, you're going to have plus on one Hg and plus on another Hg. And the chlorine, those are just the ion chlorine. So you've got a +1 for mercury and a -1 for chlorine. There's a typo there. Should do it one. Gallium, the OH is also on that polyatomic ion list. So is PO3. And okay, NH2. So if I split this out into the N and the H's, you know that nitrogen is 3 negative, so you put the 3 negative there. The charge of -1 goes here, and then you assign the hydrogen. The reason I keyed on the nitrogen is this. I'm following this hierarchy. And nitrogen is here in column 15. So I keyed on that one, assigned it a -3 first. Maybe you have to read through this to see why I did that, but I didn't automatically go to hydrogen. I went to the nitrogen because it's in this list. What it's calling group 5, the K here, is column 15 for us. So I put the column 15 there. hydrogen, if you have phosphorus, if you have arsenic, you follow that same rule. I think y'all can do these. Oh yeah, elemental compound here. So it's only got hydrogen, so you just necessarily, it's going to be an oxidation state of 2. The whole point of finding these oxidation states is so you can identify redox reactions and decide where is oxidation happening and where is reduction happening. All right. There is this, your book mentions this mnemonic called oil rig. So RIG means reduction is gain, that's gain of an electron. I should say gain of electrons. And that mnemonic works. The way I always remember this is what's being reduced, what's being referred to as reduction is a charge. Since electrons are negative, if you add electrons to something, it reduces its charge. If you can remember that, then the opposite is oxidation. Oxidation is kind of an unfortunate word. It's for historical reasons, because everybody thought only oxygen did this way back a century ago, so they called this process oxidation. So they could have called this something that's the opposite of reduction, they call it incretion or something, and then it would make more sense. If you remove a negative charge, then the charge of the thing you removed it from will go up. So oxidation is losing electrons. Its charge is going up. I think it'll make more sense if I start showing you some reactions. You can take the reactions on this page just to practice them yourself. But I go through them in the following slides. But okay, so now we have some reactions in front of you. These are all oxidation reduction reactions. And the whole point is to figure out which one of them is losing electrons and which one of them is gaining electrons. So we'll start with this one, P4. All right, so start up here at the top before you try to read all this. P4, and I've got an S there because phosphorus is solid. But notice there's only one element in this whole thing. So therefore, phosphorus has zero, a charge of 0, or an oxidation state of 0. O2, that's elemental as well. It's only got oxygen in it, so it's 0. And then those come together and we make a molecule. We make this molecule. So now we start assigning oxidation states. If you go through the process I told you, and you key on oxygen, and you wrote down 10 oxygens, you would have -20. And then over here for PO4, you would go, okay, that needs to be a +20. And how are we going to split a +20 into 4 different things? I have the sound on my phone because of what's going on with my family. Okay. That was a spam call. All right, but you'll end, if you go through the process I showed you before, you'll end up with +5 for phosphorus. You with me so far? Okay, so now we look at it and we go, okay, I have to explain this down here. So phosphorus went from 0 up to +5. That means it lost negative charge. So if you think of oil rig, that's oxidation. So phosphorus underwent oxidation. And if you look at oxygen, it started at 0 and went down to -2. So the oxygen here is gaining electrons. So it's being reduced. You with me there? There's a little bit of confusion though over these words. Phosphorus did undergo oxidation. It lost electrons. But something that's able to lose electrons can cause reduction in something else. So this thing that underwent oxidation, it has been oxidized. Read this. It has undergone oxidation. Phosphorus has. It lost electrons. It has been oxidized. But in this case, because it can cause reduction, we say it is a reducing agent. You could also say it's a reducer, and it's sometimes called a reductant. So that can be very confusing. So I list that here. I think I listed for every one of these, just so you grasp the terminology. You follow what I'm saying? Something that can give up electrons, it has the ability to cause something else to gain electrons. So these down here in red are referring to what it can do to something else. It can be a reducer to something else. It can be a reducing agent to something else. It can be a reducer to something else. But it itself is undergoing oxidation. You see what I'm saying? I know that can be a little confusing. But the whole point here is to go, okay, phosphorus is losing electrons and oxygen is gaining electrons in the course of this reaction. I guess that box down there is just me trying to clarify it. Oh, I guess I went through it in painstaking detail. But you can read that later, but this is all what I just said. All right, so here's another one. Cobalt here is by itself, so its oxidation state is 0. Chlorine by itself, so its oxidation state is 0. If you look at CoCl2 on the right side, if you try to assign things, if you split that out, you've got a negative Cl and a negative Cl. That means cobalt had to be 2+. So now you look at it and go, cobalt started at 0 and went up to +2. So that means it lost electrons, so it's undergoing oxidation. Chlorine started at 0 and went to -1. That means it's gaining electrons. You follow that?
Yeah.
Those start at 0. Have any that don't start at 0. Here's one where something doesn't start at 0. You see carbon with the S on it, that's just saying solid carbon just by itself. That would just look like charcoal, carbon by itself. So carbon by itself here with an S, so it's got a 0. Zinc over here as a solid, it's just a 0. Zinc oxide, if you go assigning oxidation states to things, oxygen is 2 negative, the zinc is 2+. And over here you have carbon and oxygen. Oxygen is 2 negative, carbon is 2+. So now you think like this. Let's see, at least one of these doesn't. So look at the oxygen. It starts at -2 and it ends at -2. So nothing happened to oxygen. It's not undergoing oxidation or reduction. But if you look at zinc, it goes from 2+ to 0. It goes down. So the zinc is reduced here. You see that? And what's being oxidized is carbon. It starts at 0 and it ends at +2. It lost electrons. So carbon lost electrons. It's undergoing oxidation. You could also say it's the reductant here. And zinc. Zinc is gaining electrons, going from +2 down to 0. So it's being reduced, undergoing reduction. You can also say it is an oxidizer in this case. Maybe we should look at some of these from the book. Let me show you this just in case you come across it. I modified this a little bit. I covered this up when I put it in PowerPoint because this is a typo. Nitrogen here is in a +5 state, not in a +1 state. So that's covered up. And I added the column numbers here because your periodic table doesn't use this numbering, 7A, 6A, 5A. If you look in PowerPoint, I covered up that typo here, and I added column 17, column 16, column 15. But I think if you just follow the process I showed you, you'll be okay with these. Everything I showed you in there is the polyatomic ions, and the polyatomic ions are covalent compounds. I think I need to move the camera. Let me go back here real quick. Yeah, let me move the camera and do a few things. There's oxidation reduction.